Good day, gentle readers. Today is September 15, 2024. Today, from a desk with Ross Finlayson, unscripted. Moment in motion. A continuing treatise, an essay in words. Audio only, though, with this video track accompaniment. The consideration is as of a discussion of a discourse on waves in the theory as a model of change in open systems, the formal, the mathematical model, as with regards to the theory of mechanics, and moment and motion as these complementary terms that reflect the inflection points of change and the state of change, the constant of change. And then as it began with consideration of the definitions of the mechanics of waves, excuse me and bless me, as with the mechanics of waves, then what so carried on forward was the consideration of waves and boundaries and vis-a-vis the open and closed systems in physics, where within a closed system there is always entirely a balance and a bookkeeping of things, or the conservation of quantity. As within open systems are any such matters of models of flow and flux and transition and deformation and the compressible and all such matters of the viscoelastic solids, in where we have a liquid model of most any sort of thing, or fluid model insofar as it is, as for example that in the time of the 1840s to the 1870s, that each of the fundamental forces were considered as of this form in their model, that it is then as of the superfluid and the gas and the frozen or the subfluid it was referred to in the solids. That then what is entailed has been a discussion of the historical setting and a discussion of today's considerations and the standard linear curriculum and a lot of the exploration into the background as arriving from our most ancient canon and our models of mathematical motion as after Zeno, and the dialectics which concentrate and center on Aristotle, toward the various considerations of all the empirical and what results the theories, since as after the Newtonian school, Galileo and Newton, classical laws, later as what arrive at the richer accoutrement of this dialectic on the vis-motrix, which is Galilean plainly, and the vis-viva, which is anything else, as to how these things arrive and arise. So today, one thing I wanted to talk about was this. So in the previous discussion, there was a mention of the Magnus effect, and it was associated with the idea that the bodies given basically compressive impetus as with regards to setting them in spin, as with regards to then setting them in motion, that there's introduced this notion of, in the Magnus effect, that it's not just as a matter of drag and lift, and also as of a sort of heft, which is a term that goes along with weight, with regards to matter, massy bodies, gravity, acceleration, mechanics of motion, weight in gravitational field, and heft. So I went to study this some more, and I should definitely clarify that it's a distinction among the greater measured effect of the Magnus effect, as with regards to its fluid mechanics and its aeronautical aerodynamics, that largely the effect that's called the Magnus effect is really as of the fluid and the aerodynamic effects is according to a model of drag and rotation in the Coriolis in the middle, as with regards to this Magnus heft is within that. So it would be distinguished that for something like the rifling of a bullet or the spiral of a football, that is not explained by the Magnus effect itself, that this is falling under this category of Magnus heft. So if there's one thing to point to that is that in reviewing sort of the formalism, the theory of whatever's otherwise usually described as effect, is that there are provided in various sources, academic most usually, the definitions of the theory and the model of this effect. And it's just to be noted that there's a note when you read this formalism. It's provided the formalism. Then there's also a note, and what it says is that there's further empirical inputs not already ascribed to this effect. Thus, there is room, it is said, for this Magnus heft, and otherwise this Magnus drag. That is just that I believe also is all of currently anything outstanding in the way of emendations, corrections, edits, retractions, or otherwise clarifications that to walk that back a little bit is that it still, of course, has this reasoning going into it as to why it is so. So that then would generally fall under what would be usually called the active force, or the vis-viva, vis-a-vis, the vis-motrix. So that way, it's just one of these matters of fact that now is so clarified. What I hope to do today was to find the dictionary of science and physics and the theories, and I was going to take a look at that for a while, and then for a little bit some of these books on the space and the extraterrestrial, as with regards to the terrestrial. There's been a lot of value garnered from this studies of the Eleatics. These two books here being basically a survey of the available fragments and their matters of discourse and some of their considerations. That these are the largely canonical inputs to our theory and as the way it's developed over time and the way it is today and how these things are and all these kinds of things. So taking a look here at the Dictionary of Science and Technology, what we are in here is this larger section of mechanics. So the mechanics is given as quite a large section in this book of several pages among the thousands and thousands of entries in this here. So where we had got to is there's a discussion of Avempace and Bradwardine as with regards to power and resistance and the initiatives with regards to the classical laws that we have today, as the classical Newtonian and Galilean laws called rest, motion, equal, opposite. And then as with regards to Newton's universal gravitation, and then the force is a function of time. So that after the equivalence principle and for frame drag, there's given this sort of explanation why the universal gravitation is kind of as a matters of reference within a larger frame, that it's within the well, as it were, the gravity well. And so the equivalence principle of general relativity is given a didactic treatment as with regards to a perceived dichotomy between what is called ether drag or ether drift and gravitational acceleration. And then as with regards to force equals mass times acceleration, that being as the definition, what's arrived at, that is well a bit the post-Newtonian. And so instead of as being as quantities, as scalars without other implicits or context, it says of that force, that definition is of the mathematical model is always a function of time. That it's always a function of time. What is this formalism as with regards to that the meaning then and the distinction enables a thinker to both maintain all the classical and keep all of the reasoning and dialectic and the all the aspects of the instrumentalist and the operationalist and the theory of physics and the theory of science and the theory, what goes into it, keeping that real, as it were, well as well with its greater surrounds, where it's a sum of histories and sum of potentials, as what's so necessary for this fuller dialectic to arrive at how we can keep the theory as it is while expanding it, that it doesn't, because it's impossible to basically disprove an enduring thing like a mathematical object, platonistically say. And it is well so that any such matters of data and experiment, as far as the entire control of the experiment, is still arrived at with the same sort of validity in accordance with their scientific method, that it's not invalidated. Thus, to get to arrive at how these laws of physics can be interpreted more thoroughly, has that, it's being arrived at these zeroth laws of physics, and taking to explain that the Newton's law of acceleration is within this wider context, to help to explain that the definition of force is similarly as so, to help explain that the classical laws as of motion and rest, and the equal and opposite is explained as with regards to the rectilinear, is where it's so balanced and conserved, this reflection, this inversion, this reciprocity, to have as well that all the unlinear defines the surrounds, that what goes up must come down, as with regards to the sum of histories, sum of potentials, sees that this richer sort of dialectic makes for it to be so that the supraclassical approach, paleoclassical and supraclassical, extra standard, can arrive at any kind of improvement at all without just wandering into a field and finding a particular application, say, with regards to this course of meeting some of the perceived requirements that, for example, Einstein brings, that the very theory of the mechanics of motion, the classical, is underdefined, and so that there's no way to disprove or disqualify anything so associated with that, but instead by equipping the wider theory with this wider context, that it's enabled and makes for itself its own enduring mathematical effect, how it can be so. So that's just to say that any other such approach would be invalidated, but that this one has this way its own carriage, all these matters of our adherence to our philosophy and our principles, physics, natural science, and then as for a theory in the theory. So from reading this entry of mechanics in this tome, and I'm not sure if this is yet Heilbrom's, let's see, it would be indicated by his initials, it is, that the bibliography of this section contains these: A History of Mechanics from 1957, and Mechanics in the 17th Century by Dugas, D-U-G-A-S, Pedersen and Pihl, P-I-H-L, Early Physics and Astronomy, 1974, The Science of Mechanics in the Middle Ages, from Clagett, Madison Press, 1959, Galileo at Work, Henkens, on Jean d'Alembert. So d'Alembert was addressed here as part of the consideration of what's called the linear fractional equations, Clairaut, and then d'Alembert in the identity dimension, this idea of x equals y equals z being singular for that, and sort of as an origin in the envelope of all these differential equations, that it was quite profound, that as with regards to algebraic geometry, that it's a very underserved and underexplored dusty corner of the Hilbert's infinite living working museum of all mathematics, that it's interesting to note it as here as with regards to Henkens on d'Alembert. Introduction by C. Truesdell to Leonard Euler, opera omnia. See also the bibliographies under force, hydrodynamics, and hydrostatics, and latitude of forms. So here was mentioned that the fluid model is considered kind of universal, and the wave model is considered kind of universal as of about that. And so it just goes to reflect that in Heilbrom's consideration of this entry on mechanics in the Dictionary of Science, that it's like this so. And then as with regards to force, as we're discussing it here, it says super classical, sum of history, sum of potentials. And then as with regards to the latitude of forms, that very well reflects these motions of the analytic, and starting with the trapezoid rule, which is measuring the rates of change in distinct differences, and for the calculus of finite differences, then it arrives at analysis and real analysis of calculus. And then as with regards to the super classical foundations of that, what we have here in these further extended discussions of at least three continuous domains, the line rails, field rails, and signal rails, their models mathematically, formally, and as after an integer continuum along the lines of Duns Scotus, and a long line continuum as of Dubois-Reymond, with an averral to the infinitar calcul and the space of all expressions, all real valued expressions. That thusly the continuum mechanics for the simple conservation law, and then for the high and low energy in the near and far field, make for these things, and that otherwise the continuum mechanics and the mechanics and dynamics of discretization and aggregation have these doubling and halving spaces, which are so relevant, profound, and underexplored, yet as well that these coefficients show up in the systems as arbitrary, yet what add up. So then we are talking to pick up after Avempace. And although they may look like applied mechanics, these laws belong to the scholastic tradition. And then he mentions nominalism, which is kind of the idea of like, well, in our scientific discourse, we can make a model of things and a mathematical model of things, and we hope that it's representative of what then we can sense and measure of the physical model of things, and as with regards to our mental individual models of things. The nominalism is just like, well, if it doesn't work, then maybe something else does. Whereas with this, the idea of Platonism and the strong mathematical Platonism is that there's one that it is. And so then the ones we have as nominalism are just kind of as we seek to attain to these, then what we may obtain vis-a-vis a plainly non-thing. So that's just to mention that the philosophy of nominalism, or fictionalism, as sometimes it's so related, is very important to be able to pick up and put down things without coming too attached to them, so that you don't necessarily make an ontological commitment which is later retracted, because then that calls into question any such matters of belief. And so the idea then, though, that there is this wider theory where it is so that is strong, and it's mathematical, and it's Platonistic, and it provides logicism, and it provides positivism, that then these other reasons why we distinctly, formally make a separation from the whole entire world of the abstract, as with regards to then that's all still available under all such matters of contingency, just helps to explain that these are the kinds of issues that have defined the philosophy and the reasoning of a lot of people. There's like, we can't have any metaphysics or philosophy involved at all. That there still is this idea of the silver thread as like a theory of truth, real truth, true truth, all the way through to what we can attain to. That this way there can be altogether this holistic comprehension of things, which otherwise would be lacking. Otherwise, there's no reason to give it an ontological commitment at all. So this way, you can take it or leave it. You can pick and choose. You can make of it what you will, as with regards to there's still this wider, more thorough dialectic where it is what it is. All in theory. Mathematical statics was pursued during the Middle Ages, primarily by the school of Jordanus de Nemours, who introduced the concept of positional gravity, or weight as modified by the constraints of the system. So this will often come up as momentum. So momentum has that, it's relatively recent, as with regards to that, within hundreds of years, relatively recent. Vis-a-vis inertia. And so inertia is basically the multiplication of mass times velocity, because it provides for equal and opposite reaction. And then when we get into force equals mass times acceleration, then it gets involved that inertia and momentum are kind of related. And so why the classical relation has in the middle a particular relation to momentum, according for force and acceleration, instead of inertia, is kind of a thing. And so when you first learn, or when I first learned inertia as mv, mass times velocity, I was like, this is, perfectly linear and suited. And then it became that when the momentum was like, well, it's 1/2 mv squared. I'm like, oh, you mean just like if you took the derivative of that? It's like, well, yeah, it's kind of like one's the antiderivative of the other in terms of then what must be this system, of this differential system. And as Einstein puts it in his theory, that the theory is an inertial system and a differential system. It's all parameterized by time, so we have dynamical modeling of the whole thing. That momentum and inertia then come into play as various, because the idea then that momentum is what's conserved, and vis-a-vis the inertia what's conserved, kind of touches on a couple of different things with regards to them being linear qualities and quantities, and as with regards to them being which one is central, which one is in terms of the other, which one is derived in terms of the other, which one is implicit in terms of the other. So with regards to these notions of like the positional and gravity and all the different things that go into the active force, all the kinematics of the body, vis-a-vis its plane, kinetic, centroid, rectilinear, linear consideration within as a model of an ideal particle, essentially, or the billiard ball mechanics, has that this distinction between inertia and momentum is at once providing for this severe abstraction to lead into the where it's central, the force and mass times acceleration, yet as well that is, while it's peripheral, the inertia, it is still kind of the true inertia. So here with the ideas of the notions of the centripetal as a model of the forces in effect with regards to that which would be an open and closed system with otherwise a free rotating system, and the centrifugal as a fictitious force, has that this true centrifugal then relates to this distinction and a contradistinction and juxtaposition of inertia and momentum. Here as was introduced as inertial momentum, momental inertia, with regards to that in our mechanics, it's an inertial system and it's a differential system. As with regards to the differential character of momentum, here is with regards to that being considered the conserved quantity, as with regards to the pseudomomentum and among the open systems, or it's conserved in the open, as is put here, why it is so that it can be looked at the same and then differently, the momentum and inertia, to replace inertia as the central concept, and the resistance for something to change, what is necessary of the inputs that arrive to it, vis-a-vis the potentials it carries, only as an individual within the entire system of all the other objects with all the potentials they carry. So inertia and momentum and inertia have things to be figured out with regards to each other. And then as with regards to the definition of the quantity, and that it looks just like this one's linear and this one's its derivative, and this one's linear, this one's its antiderivative. As with regards to then that sort of modeling gets into why sometimes it doesn't really sort of make sense, the usual linear development of inertia and momentum, and then it's just brought in, it's like, here's all these formulas to derive momentum, and here's how we relate it to the angular momentum, because the winding of the wheel and all these kinds of things that go into that are underdefined. Newton has left everything very much classical. The apple falls straight down. Einstein, he very much kept it then with regards to the gravitational tensors, and this is like, well, we just kind of live in a well, and then everything kind of has always the force connecting it, but how that goes over the course of the things, you might as well call it a hypercube distance, because Zeno's swath takes that corner or the straight line either way that it is. If we row far enough of the river, then whether or not it floats back down, or which is the fastest way there and back without losing position given the flow, unidirectional. These are the kinds of things that make for the wider surrounds, and so that it's still the same theory, reinterpreted as with regards to this dialectic, the didactic deliverance on these different concepts, how they relate, and then providing the mathematical models to get back from what was lost information to what information would have to add up to make it back. So inertia and momentum are underdefined terms, but inertia is more easily defined, and then momentum is kind of an emergent term. But momentum in these other systems is more easily defined, and inertia is a derivative term. Figuring out then how this the laws of conservation are to apply, because that's one of the principles of physics, and it's inviolable. It's in accordance with what is. As that is so, that there are, of course, many people who've considered this as with regards to the superclassical notions like the pseudomomentum, and ultimately in some of these things like with regards to something like the pseudodifferential, which is still true. The moment reflects a truth, like this true centrifugal, or the elementarily deconstructed and reconstructed differential, and as to why then that is part of our fuller accoutrement, where motion and change of objects, various contents as open systems themselves and closed systems themselves, have that this infinitely many higher orders of acceleration, or the infinitely many higher orders of acceleration, all live in one thing. And so then when trying to reconnect, when it's just like a simplest two-body system, equal opposite, where things are otherwise the same, or as with regards to one being an unstoppable force and the other being an immovable object, it's to be arrived at then these things as to why then everything just kind of lives in a fall of gravity and orbits, and it's the same as the universal law of gravitation, and with regards to the system and the theory writ large. Mathematical statics, the Middle Ages, dynamore, positional gravity. Weight is modified by the constraints of the system. So here that's considered as with regards to the hypercube distance and the infinitely many dimensions that contribute to each nominally non-zero yet vanishing bits that then in the major components result finite quantity. Jordanus resolved the weight of a body supported on an inclined plane into components parallel and perpendicular to the plane. He obtained the law of the balance or lever by calculating virtual displacements from equilibrium of the weights considered positionally. His approach, transmitted in the Renaissance by Peter Apian and Nicola Tartaglia, influenced Galileo and Simon Stevin. Stevin distinguished clearly between statics and kinematics. Study the motions of bodies without regard to the agents of motion. So the kinematics, here it's kind of distinguished the kinetics and kinematics, because kinetics is kind of like a measure of energy, and the kinematics is the dynamics according to levers as being everywhere, and that the lever is the simplest machine, and then it's also defined as a model of a centroid, of a system under any such manners of rotation. And so in our three-dimensional space, it's just to go that here I'd want to figure out how that kinematics, the study of the motions of bodies without regard to the agents of motion, has that's kind of like a severe abstraction, where the severe abstraction, of course, was introduced as whatever is the simplest formula that results that still gives a number, without necessary regards at all to any such other matters of empirical input or dynamics. So Simon Stevin, the famous Flemish person, so freed statics from unnecessary complications introduced by analysis of virtual displacements. Here, this is with regards to the notions introduced of the absent displacement and the virtual displacements. Displacement occurs only in approach to equilibrium, and its application to statics hold only as a non-physical limiting case. Stevin formulated a statics independent of such kinematical concepts and provided a basis for the generalization of the principle of virtual displacements. See here, that's accepted as linear and kind of classical, with regards to that there's great interest in the wider surrounds, the many-body problem as with regards to the two, or the way that it's possible to consider the adiabatic and the non-adiabatic. The other day I procured a book, and it was from 1846, so I mean it's from 1846. And it's a World Fact Book from 1846, and so it's produced in London, and it's a bunch of excerpts from some of the great journals of the day, like the Athenaeum, where Faraday every day or week would read out a new article of discovery of great scientific import, or the Jamesons with regards to all such matters of things that go on in the studies of wells or geology or agriculture and these kinds of things. And so what I'm reminded of that is as of with regards to that the concepts in these kinds of things that it helps to reflect that what I wanted to mention was this. Our theory of chaleur, or heat, is as according to Fourier style analysis, and it was read here as with regards to adiabatic and the limiting case and the unidirectional and all this kind of stuff. So some of these experiments described they had like layers and the passage of heat through layers of lacquer or otherwise different material properties. And it helps us show that these waves in layered media can also start to add up, that there is a course of consideration of the thermodynamics that relates here mostly the considerations of the second law, which is today all the basis of the statistical ensemble, kinetics of the thing, and the Fourier style analysis and a heat equation vis-a-vis the caloric, which is much more of this notion of that we've got a fluid model of it, so it involves the back and forth and the currents and eddies and whatever is as with regards to dynamics within the fluid. That is just to reflect that this is the sort of thing where making a severe abstraction to this virtual displacements or their absence thereof, then keeps things real simple and nice and neat and linear, and thus tractable. But it's not always the case that results sensible. These are some of the definitional dynamics in play, as with regards to yet a simple system where everything classical is still just falls out as what it is. In our classical models that still hold up under the control of their setting and configuration energy of experiment, that still the entire more unlinear universal concerns are as well included as for what they are really. So yeah, that's what I wanted to mention with regards to the studies from 1846. It was a time of great scientific progress, and very regularly many new astonishing things were discovered, as with regards to, for example, the dynamics of materials and states of matter, and with regards to the magnetic and all these kinds of things as well. That it was an interesting time. Galileo took an Archimedean approach to the schoolman's problems and conjectures. In De Motu, on motion, he attempted to amend Aristotle's treatment of motion by using Avempace's rule and Burden's concept of impetus. He thus rejected the impossibility of vacuum, the existence of levity, and the strict differentiation of natural from violent motion. Both involve acquisition of impetus. So here that says with regards to the tendencies, where it's considered as something will just go the way it's going to go, and propensities, which is something is given to it to make it have a current or potential or future result. He thus rejected the impossibility of vacuum, the existence of levity, and strict definition of differentiation of natural from violent motion. At the same time, he kind of disqualified either of those sides. He said, "Well, how are you gonna distinguish between the two?" He's like, "Forget the other." By 1604, he had broken more fundamentally with tradition by making his goal a quantitative description of an apparent oxymoron, ideal real motion. See here, it helps to establish that the term's underdefined, and so it's something as of both practical interest and theoretical interest, in both ways. Ideal real motion, which he supposed would occur if air resistance and other usually small disturbances did not exist. In general, Galileo analyzed motions, not their causes. He consequently sought and sometimes misidentified cases amenable without reference to causes. An example is his claim that bodies show no effect in virtue of their participation in the Earth's motion, a principle essential to his defeat of physical arguments against heliocentrism. You know, these days it's kind of, there's the Lense-Thirring experiment, so they launched it to space, right to the edge of the gravity well, and they're like, we measure frame drag, ether drift equals escape velocity, also kind of matches up with motion, which happens to kind of be the same for y, maybe because it's a thing. It's a windsock of sorts that measures the velocity of the Earth around the sun. And then the Parker probe that was sent to the sun. Then it's like, well, yeah, and the sun is flying around the galaxy a lot faster. So you can kind of pick up this relative motion according to the largest body in the system. To us, it's Earth. To the Earth, it's the sun. To the sun, it's its galactic arm. To the galaxy is just a disk, but it's rotating free. This is one of these great things that helps establish part of the cosmological study of it. But here is with regards to Copernicus and the Coriolis effect, which is found, and if you launch a projectile far enough along, it will have entered its own space frame and frame space, and re-entered its own space frame and space frame space, as with regards to projectiles and their destinations, as with regards to all being about as matters of orbit in their trajectories, vis-a-vis Galileo's great success with the notion that the otherwise entirely linear projectile has a parabolic path of motion that Newton later used to demonstrate the inverse square is the opposite of a parabola, and so obviously it's the formula, and that also then that later that it was arrived at the or earlier rather, that the 45-degree angle gives the maximum distance, vis-a-vis that if for an item in flight, as long as it can maintain any sort of heft or otherwise independence or resistance when it radiates as it goes on out the way, then is when it arrives down that there are variations of this, and they're very well explored in the empirical setting. Not that I don't know too much about them. About such notions as the notion of ballistics is usually this field. So, Galileo, an example is his claim that bodies show no effect in virtue of their participation in the Earth's motion, principle essential to his defeat of physical arguments against heliocentrism, or, to the side, as it were, Copernican revolution, but inconvenient and even contradictory to his chief argument in its favor, the tides. So the Coriolis and the tides and the tidal action here is described basically in reflection of this. In the ancient times, there are two scientific facts, and one was the application of the lever, and the other was the displacement of buoyancy in water according to displacement. So that's kind of like the tidal versus the classical here is this kind of thing. Another associated principle is circular inertia, which Galileo sometimes substituted for Aristotle's natural motion in the Dialogo. Although he doubtless did not perform the demonstration from the Tower of Pisa, this is a ball of iron and a ball of wood. He dropped them at the same time. They land at the same time, neglecting air resistance because they have the same outer form. Has that actually, the massier object will end up falling faster over a longer distance? Just that otherwise it's a universal law of gravitation is easily demonstrated in this configuration of experiment. Galileo certainly confirmed his principal results, which were identical with one form of the Newtonian rule, by experiments on inclined planes. This is as with regards to the tautochrone, and as well that it's kind of the same kind of setting with regards to how long the path is, and as with regards to its reaching many or more minima and maxima, or the roller coaster vis-a-vis the ramp, that again Galileo was able to show up to, according to all known measurements, there was no differentiating these two, and he picked one form of the Newtonian rule, and that also that as to whether it was linear or derivative or linear and antiderivative to the other, helping to make a formulaic approach that used a lot less paper, was a lot less easier to mentally catalog, and these kinds of things. It's the way of the things. Although he doubtless did not perform the demonstration from the Tower of Pisa, these results in free fall velocity v and distance s are respectively gt and gt squared over 2. So this helps affect a lot, again, this inertial and the momental, and I was delighted to read this phrase. It says that the associated principle is circular inertia, that here I'll be looking to study some more and find out some more about it. Combined geometrically with the consequence of Galileo's impetus theory. Without resistance, a violent motion will persist with constant velocity. So this is already introduced motion, rest, and then as with regards to equal and opposite, that must still be just given as kind of a given, or as with regards to it's the Newtonian rule at this point. Galileo gave many theorems about ballistic motion and discourse, but the degree of abstraction made the results impractical. Here, practicality isn't the primary concern. The the definition of the qualitative aspects have to expand the vocabulary to include the wider dialectical setting. First, Zeno's definitions for continuous motion, continuous time, giving that a realm for definition vis-a-vis this degree of abstraction, and as to whether sometimes a degree of abstraction is more or less. So, Galileo's revolutionary concern with ideal real motions became the theme of progressive 17th century mechanics. Descartes, among others, insisted on the principles of relativity of motion and of rectilinear inertia. Many corpuscular philosophers sought laws of collision to describe the encounters of billiard balls. So this helps relay that this was the means of discourse and the common dialogue and the common lexicon, and as well what made sense practically to the intuitive, because these were then providable as the conditions under which things could be experimented with and repeated, observed, and as not apropos falsified. Descartes provided too many such laws and placed them at the head of his Principia Philosophiae. They were amended by others, notably Christopher Wren, John Wallis, and Christian Huygens, who you can definitely count among the pyramid scheme of Newton, who also gave the first published expression for the centripetal acceleration required to maintain constant circular motion in the Horologium Oscillatorium, 1673. So Huygens' principle, we got these waves, and waves make waves, and a bunch of these kinds of things. As with regards, you can kind of think of that as like the geometry and as about a circle, and as about outside, it's like an Escherian or the Riemannian geometry. On the outside is you just do space inversion on that, and it's as of the opposite of it. So these matters of projection and perspective help to go to effect to reflect that before the swing in the bucket was centrifugal, and it still is its own thing, as with regards to whether or not the axle that it goes around is immovable or unstoppable. These kinds of things. So does that introduce too many definitions, as it's mentioned Descartes did? Well, it's kind of like here where it's like you got tendencies and propensities. Either one indicate potential. There's attenuation and dissipation. Both indicate something that goes away. And then there's oscillation and restitution, and both indicate something that stays. And then as with regards to this discord on motion and rest, it's not introducing too many terms, yet as well just to provide a commutative diagram or otherwise a category diagram as to how they go around is kind of the idea, vis-a-vis getting into, define the infinitely many higher orders of acceleration, which must exist because 0 meters per second is infinity seconds per meter, and to bring that into a mathematical model, again, without so many more terms than this. These long-winded discussions of this overall utterance have not filled more than a few days of listening. It has got quite a lot in it. I hope this seems as gratifying to the development of these concepts as they go along, because they're the same ones. This is our canon, this is our dogma, these are our lions, these are our giants. Us. Who also gave the first published expression for the centripetal acceleration required to maintain constant circular motion. Contrast with circular inertia, and as with regards to free rotating frames. The postulate of composition of velocities used implicitly by Galileo in his derivation of ballistic trajectories was made explicit by Pierre Varignon and Bernard Lamy, L-A-M-Y, Lamy. The principle of conservation of a vector or directed momentum emerged clearly from this work. So Varignon and Lamy, or Lamy, I'm not quite sure how that's pronounced, have that, referring back to this earlier notion of the inertia and momentum, that the principle of conservation of a vector or directed momentum emerged clearly from Varignon. So Varignon will deserve great inspection to help understand and comprehend what deliberations and ponderances he made among the milieu of these other developments to help express that it can be rehabilitated in a sense what it means to have this conservation otherwise of the quantities which are associated with the things of peace vis-a-vis what results something that's fungible, directed momentum, and as with regards to otherwise these systems in their dynamics. So this can be, that is something that I'll be looking to study that a little bit more, because trying to understand the distinction and contradistinction and juxtaposition and complementarity of inertia and momentum, and as it's called here, inertial momentum and momental inertia, here is with regards to things like circular inertia and the true centrifugal, vis-a-vis what is expressed as centripetal acceleration, constant circular motion, vis-a-vis a sort of free circular motion, or something along the lines of a driven circular motion, that these will be the things. Varignon, 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 1654 to 1722. Most of these principles, rectilinear inertia, composition of velocity, conservation of momentum, were formulated or reformulated in or around the three axioms of motion, with which Newton began his Principia, a synthetic work capping the tradition begun by Galileo. Although Newton concerned himself with the nature of body and force, he tried, not always successfully, to give his results in the Principia in terms of velocities, accelerations, and other ideal, real observables. Well, that's basically the development today, is the definition of momentum and the under-definition of momentum. So introducing an under-definition is kind of helping to explore that these concepts, as they're arrived at, had all these things that went into them, that then they result something that's fungible. You can pick it up and put it down. It has its minimal sort of ontological commitment, so related in these relations, these derivations together and assembled, that it's as of its own discernibility and its own way to make it so fungible, and thus to make things tractable while keeping things sensible. But how it arrived at being sensible is all these other considerations that also have their own reasons why they're sensible. So the under definition is after a sort of this severe abstraction vis-a-vis what's called an overloading of the terms. So there's much to be said for reasons why, that then investigating Varignon, and then later the association with Galileo and Newton's laws of momentum, and where the whole idea of conservation of momentum came to be entered in as the quantity, and made a kind of distinction between what are considered real forces and what the balance of things are only called fictitious or virtual forces sometimes, has that there's not necessary that distinction to exist. So trying to figure out how to help frame it in an overall sum of history, sum of potentials, is a reasonable modern course for this kind of consideration of matters of definition. Newton is often put up as the poster hero of one of the greatest aspects of science. They got to work in theory at this point. Although Newton, the Principia established the basis for the theory of motion, of mass points under centripetal accelerations in absolute space, and set the problem of treating a system of bodies interacting via accelerative forces diminishing in strength as some power of the distance. So here we're deconstructing this and talking about the hypercube distance equals 1. And all these kinds of things that go into it as is with regards to do objects gravitate? It's like the orbit in a gravitational field, which we call the gravific. It's kind of true centrifugal vis-a-vis the true centripetal gravitic. And so this is just helping to establish that why this is so great, this definition of motion for mechanics, because it keeps things simple for then an introductory linear curriculum without like the entire dialectic of what goes into things. Here with what the goal is to be able to put that out as both together, what otherwise either without the other one is lacking full definition, and the other is lacking tractability. And set the problem of treating a system of bodies interacting via accelerative forces diminishing in strength as some power of the distance. It's shown in the case of gravitating spheres and spheroids how to obtain observed macroscopic effects from assumed microscopic causes. And as an aid to destroying Descartes' theory of vortices, which here we can bring back, subtle matter is this concept. It gave an approximation to a quantitative theory of motion in resisting media. A byproduct was a novel theory of the propagation of sound, which gave its velocity as a function of the pressure and density of the medium of conveyance, or waves. Let's see here. The 18th century systematized and extended Newton's approach and synthesized it with the mathematical methods of Leibniz and Johann Bernoulli I, who generalized the principle of virtual velocities into the anchor of statics. Leonhard Euler subjected the dynamics of mass points to analysis in his Mechanica, building on the work of Daniel Bernoulli, Alexis Claude Clairaut, and Jean Laurent d'Alembert. He also devised the fundamental equations for the flow of inviscid fluids, and through such concepts as moment of inertia and instantaneous axis of rotation, he made the theory of the motion of rigid bodies, Theoria Motus Corporum Solidorum, 1760. So about 80 years before this milieu of the 1846 World Factbook in Faraday's day. Another systematization occurred through synthesizing principles apparently opposed. After a long dispute between partisans of Leibniz and of Newton, agreement was reached about 1740 on the proper measures of the force of moving bodies. Momentum and vis-viva were recognized as different integrals of the second axiom of motion, and the property of Leibniz's principle of the conservation of vis-viva acknowledged for elastic collisions. Well, that's great. Then that just helps to explore that is one of these branches, or where the singularity theory is a multiplicity theory, and that it is where this distinction is so kind of kept. Here, as with regards to then this fuller theory, as with regards has been discussed here before about that distinction, vis-motrix and vis-viva of Newton and Leibniz, that's not all there is to it. There's further branching involved. So with the idea of underdefining momentum, underdefining and overloading and deconstructing, that the entire idea is that the deconstructive account and its fuller dialectic is what makes it possible to revisit these ideas and reestablish the needful, so that then the fuller theory ends up getting further and further together instead of further and further apart. Well, gentle readers, fellow earthlings, that's what there is for today. Basically, a consideration of why pseudomomentum is a thing. And as with regards to that why is because it was defined somehow. And the reasoning that goes into why and how it is defined has further considerations on how it is, and and also in the ways that then it can be made sensible and fungible and tractable with regards to these tendencies and propensities, this attenuative and dissipative, the oscillative and restitutive, the constitutive and reconstitutive and deconstitutive, which results as sum of history's sum of potentials as the real fields, whereas what goes up must come down, and it goes around and around. Good day then.